All right, module number 24, integer programming. Here we have an interesting constraint that we're requiring the solution to fit on a grid, an integer grid. So we have an optimization problem where the variables that we're solving over must be integers. Now, of course, when I'm saying integers, I really mean discrete. Any grid would be fine, but let's just think about this as integers. It'll be simple enough. So an integer linear program, ILP, has the following form. X star or X hat, the optimal X, is the argmax of C transpose X, subject to, first of all, we want AX to be equal to B, and we want X to be an integer, and by integer, we denote that by X is an element of the set Zn, Z for integers. However, because because A times an integer valued X may not be exactly equal to B, we have slack variables S. And in our integer linear program, we allow S to be positive, okay? So we're maximizing C transpose X subject to something that's close to AX equal to B with the slack. All right, so again, why can this be useful? Let's talk about an example, and our example will be support set detection. Y equals AX plus Z, and we're searching for a sparse X. What does sparse mean? Sparse means that we're searching for a solution X to Y equals AX plus Z such that the large majority of the values in X are 0. Why would we want to do that? For example, in a machine learning application, it could be that we want a simple explanation, and an explanation that has a small number of non-zeros. So in other words, we want to identify a support set where the locations of X are non-zero. So it's the support of the non-zeros of X, and the rest of the locations of X are going to be zeros. And we want the support set to be small. So what we're really looking for here, we're searching among the sparse X's with a small support set, we're searching for the ones that explain Y equals AX plus Z, explain it well. Well meaning that Z, the noise, presumably noise, will be small. So we're looking for a sparse X such that A times X will be close to Y, meaning that Z will also be small. Can we do perfect support set detection? So suppose that we're given the noisy measurements Y. So X is unknown, A is a matrix, we know A, and we're not measuring A times X. If we were, then it would be a much easier problem, but we're measuring a slightly noisy version of that. So Z presumably has a small amount of noise. And can we identify exactly the locations of the non-zeros in X? So yes and no, it depends. If there are non-zeros and all the non-zeros are large, this problem is less challenging. On the other hand, if some of the non-zeros are tiny, that would mean that you can explain them away with a bit of noise in Z. So if they're tiny non-zeros in X, this is a harder problem. What about the signal-to-noise ratio? If we have a high signal-to-noise ratio, meaning that the noise in Z is small, this is an easier problem. If the signal-to-noise ratio is poor, meaning a lot of noise in Z, this is a harder problem. So in words, when there are tiny non-zeros, you're more likely to make mistakes. When the SNR is poor, you're more likely to make mistakes. Performing perfect, in quotation marks, perfect meaning always, support set detection, in the noisy case, that's impossible because you could always by mistake have noise that's pretty bad. So, okay, what can we do? So we want to perform support set detection, and we want to find a good support set. So here's a possible algorithm. Consider a candidate support set. So for every location, recall x is of length n. For every location of length x, decide whether it's in the support set or not, and denote this support set vector by a vector s, and s will be a length n binary vector. So for every location, if s is 1, we're allowing x to be non-zero. If s is 0, we're not allowing that. So now we can contain a matrix AS that we're bunching together the columns of A that correspond to locations in S where that value of S is 1. Locations in S that are 0, we don't look at that column in A. And now we have a hypothetical support set S. For that hypothetical S, we've constructed a matrix AS that contains the corresponding columns. And we're now asking, is it reasonable that we'll have an X that corresponds to that support set? So in other words, and it might have been more clear if we would have called this XS. So we're looking for an XS whose length is presumably less than n, presumably the support set, the number of ones in the vector S is much smaller than n. We're looking for XS such that AS times XS is close to Y. Now, it's close to Y. It's not really equal to Y. So equal will be kind of in quotation marks. So I'll just write a question mark here. So it's probably not equal, but maybe we'll have a low energy solution that's close to Y. So here's our approach. We're going to loop over all the possible S vectors, and we have 2 to the n of them, and we're going to select the solution that's closest to Y. Now, this algorithm can be shown to be optimal. It has various optimality properties. In terms of optimal, meaning finds a good solution to the support set detection problem. However, it's very slow. Because recall when we were talking about computational complexity, here what we're doing, we have all the possible support sets, and we have 2 to the n of those. And for each of them, we're solving this least squares problem. We're concatenating the corresponding columns. So for each of 2 to the n problems, we have a polynomial complexity algorithm. So the overall complexity here is exponential multiplied by polynomial. As we've discussed before, maybe we can solve this for problems of size, let's say n equals 20, but not much beyond that. Okay, so what can we do? So we have this integer linear program, and it can be shown to be in the class of NP functions. Now, what is the class NP? It's a class of algorithms that, on the one hand, we suspect that their runtime is exponential. We believe that it cannot be done in polynomial time, but this hasn't been proved formally. This is a long-standing conjecture in theoretical computer science, and people are extremely confident that, that these algorithms indeed require combinatorial runtime. All right, so integer linear programs, if you can solve it optimally, it probably requires combinatorial runtime. On the other hand, maybe you can solve it near optimally. So for many of the problems that are NP, there are approximations in polynomial time. So one of these approximations, specifically for an integer linear programming approach, is called relaxation. We begin by ignoring the integer constraints, and we solve a standard linear program. After that, we have a non-integer solution, presumably. If it's an integer solution, perfect. And presumably it's a real valued solution, and we round it to a nearby integer solution. Now, it may not be the nearest. It may not be like actual rounding. It may not be rounding to the closer one. If we're, let's say, 4.3, we may try to round it to 4, and we may also want to try to round it to 5. So you can imagine that we solve this standard linear program, and then we kind of try to wiggle around it in locations on the grid that are nearby. Now, there are various applications that require integer solutions, and I just want to mention that we just skimmed the surface here. So that'll be it for this module, and we'll continue next time.